In this video, we're going to look at how to calculate acid-base equilibria. So the types of problems we're going to go over here are a problem where you would be given the equilibrium constant for a given acid-base equilibrium, and you would be asked to solve for the equilibrium concentrations of the species involved and or the pH of this acid-base reaction. So we'll work a couple of problems to help illustrate this, but it's important that you are able to recognize these types of problems when you see them and apply the appropriate strategy to solve them. So let's work a couple of problems. Before we do, I've written down some steps that I like to follow when I'm solving this type of problem. If you would, take a minute, just pause the video and write these steps down so that you can follow along as we go through the problem. So let's look at one problem. It says calculate the pH and the concentration of all species present in a 0.05 molar hydrofluoric acid solution, and you're given the Ka for this weak acid, 3.5 times 10 to the minus 4. So like we said before, in this type of problem, you are given the Ka value and you're asked to solve for the pH and some of the equilibrium concentrations. So we're solving for the equilibrium concentrations here. So the first thing we want to do is let's write an equation that represents this equilibria. Pause the video and see if you can do it. So we have hydrofluoric acid in water. Hydrofluoric acid is an acid, so it will lose a proton to form the conjugate base fluoride, and the proton will go to water to form hydronium. So if you would, before I go through this problem in detail, pause the video and see if you can solve this problem. See if you can calculate these equilibrium concentrations before we go through it. Pause the video and give it a try. So the first thing I want to do is set up an ice table to help me keep track of my concentrations. So you can see I have the initial concentration, change in concentrations, and equilibrium concentrations on the left, and my acid-base equilibria up top. Next, let's insert our initial concentrations. We're given the initial concentration of hydrofluoric acid. Water is a pure liquid. We don't have to worry about that. The hydronium ion concentration is approximately 0. There is a little bit in pure water, but it's very, very small. And initially, there is no fluoride present. Let's determine the reaction or the direction the reaction will proceed. We can see that our products, the concentrations are 0, and so the reaction must proceed initially from left to right in order to reach equilibrium. Let's determine our changes in concentration. We know it's going from left to right, so my reactant concentrations will decrease and my product concentrations will increase. And we look at our stoichiometry here, everything is a 1 to 1 to 1 ratio. So we have minus x, plus 1x, and plus 1x here. Next, let's fill in our equilibrium concentrations. This would be initial minus the change here, and initial plus the change over here on the product side. Next, let's write an equilibrium expression for this reaction. We know our equilibrium here is an acid equilibrium. We have a weak acid, so we're going to use Ka, not Kb. And we're going to have our products divided by our reactant concentration, everything to the first power. So it would look like this. Next, let's enter our equilibrium concentrations, which we have in our ice table. So we're going to plug these values into our Ka expression. Again, we use Ka when we have an acid over here on the reactant side. So we plug those in and our equilibrium expression looks like this. And now we can solve. In this case, we're going to need to use the quadratic equation. So I've just gone through the algebra here to get everything in the correct form. Ax squared plus bx minus c equals 0, so we can use the quadratic. Again, I went through that kind of quickly, so pause the video and again, be sure you understand those steps. Now that we have it in our quadratic equation form, we know that our A value is going to be 1. Our B value is positive 3.50 times 10 to the minus 4. And our C value is negative 1.75 times 10 to the minus 5. We'll plug those into the quadratic equation and solve for our two values. So here you can see I've set up my quadratic, plugged values in. Solving it, I get my two values for x. Only one of those can be correct. We can see that x is a concentration. X is the concentration of fluoride and hydronium at equilibrium, and we cannot have a negative concentration. So this value, the negative value, cannot be correct. So our value for x is 4.0 times 10 to the minus 3. So that gives me my hydrofluoric acid equilibrium concentrations, 0.05 minus x, and my concentrations of hydronium is equal to x, or 4.0 times 10 to the minus 3, and fluoride equilibrium concentration is the same. Now we were also asked to calculate the pH. The pH is the negative log of hydronium. We have our hydronium concentration. Take the negative log and I get 2.40. Now that is an acidic pH. We have an acid, so that makes sense. And also we want to calculate hydroxide. Hydroxide concentration, we can calculate that by taking our Kw value, it's a little messy, divided by, in this case, the concentration of H3O plus. So it's a little hard to write here, but you can see hydroxide ion concentration is equal to Kw divided by the equilibrium hydronium ion concentration. So now we have our hydroxide. And the final thing, let's just check our work. It's always good to check to be sure we did everything correctly. We have our values. Let's plug them into our Ka expression that we had earlier and solve for Ka. So again, we're plugging in our equilibrium concentrations because that is an equilibrium constant. Plug them in and solve, we get 3.48 times 10 to the minus 4. We were given Ka at the beginning of 3.50 times 10 to the minus 4, and you can see there is a pretty good agreement between those two numbers. Maybe a little bit of rounding cause for this deviation. So we can be pretty confident that we have the correct concentrations and the correct pH. Let's take a look at a second problem. In this problem, we're going to look at a weak base instead of a weak acid, but the overall steps are identical to those that or very similar to those that we did with the weak acid. If you would, read through the question, pause the video, and give it a try. See if you can do this on your own, and then I'll work through it with you. Okay, so first thing, let's write our equation. We have a weak base, and what I've done here, I've just, for simplicity's sake, this is the chemical formula for my weak base. I've just used B for base to substitute for that. However, this is a base, so it will accept a proton, in this case from water. So we will get our weak base will be Hb plus, or C4H9NOH plus OH minus. So this would be the equation. Be sure you can write these equations readily. And now let's set up our ice table in order to keep track of our concentrations. You can see we have our base equilibria up top, our concentrations over here. Let's plug in our initial concentrations. We're given the initial concentration of morpholin. The water is a pure liquid, so we don't have to worry about that concentration. And my initial concentrations of my Hb plus, my conjugate acid, is 0, and hydroxide is approximately 0. Again, there's a little bit, 1 times 10 to the minus 7 molar from water itself, but approximately 0 compared to this concentration. Let's determine the direction of the reaction. Now, initially, we have no Hb plus, and so we know the reaction must proceed from left to right initially in order to reach equilibrium. So that helps us determine our changes in concentration. We'll have minus x over here, plus x and plus x over on the product side. And again, all our stoichiometry is 1 to 1, so everything is 1. Now let's get our equilibrium concentrations. That's our initial minus the change over here, and the initial plus the change over on the product side. Let's write our equilibrium expression. Now be careful here. Here we have a base in water, so we need a Kb expression. The overall formula is the same as a Ka expression, the overall setup, but this is going to be a Kb. Now let's plug in our equilibrium concentrations into our Kb expression, and our Kb value was given. Now we can solve it. Let's solve it and get it in the form of a quadratic expression. Here we have ax squared plus bx minus c, and that gives us our values for our quadratic equation. Our a value here is 1. Our b value is 2.09 times 10 to the minus 6. And our c value is negative 2.09 times 10 to the minus 8. Let's plug those into the quadratic equation and solve. You can see we have it plugged in here. If we solve, we get two values for x. Only one of those can be correct. Again, x is equal to our concentration of Hb plus and OH minus, so we cannot have a negative value for x. So x must be 1.44 times 10 to the minus 4. So now we can use x to plug in here to solve for our equilibrium concentrations. So 0.01 minus x gives us the equilibrium concentrations of our morpholin, our base. Our Hb plus would be equal to x, and our OH minus would be equal to x. We're also asked for the concentration of hydronium, so we just take our Kw divided by our concentration of hydroxide to get our hydronium ion concentration. When we have the hydronium ion concentration, we can take the negative log of that to get the pH. We get a basic pH, 10.16, and that makes sense because this is a base. So again, that makes sense. Let's check our answers to see if we're correct though. Let's plug our equilibrium concentrations here into our Kb expression and solve. If we solve that, we get 2.09 times 10 to the minus 6. We have our Kb value was given earlier in the problem, and it's the same. So we know that these must be the correct concentrations because we have a perfect agreement between our answer. So again, with these types of problems, be sure you can recognize the problem when you see it. You're given Ka or Kb, ask for the equilibrium concentrations. And when you recognize it, be sure you can apply the appropriate strategy, those that we showed you here, in order to solve.